Welcome to the 10th lecture. So, this lecture we will be discussing in this lecture MIPS programming examples. So, we will start with how a C code, that is a code written in high level language, can be converted into MIPS 32 code. So, this code is A equals to B plus C. This code can be converted into S2 plus S3, the result will be stored in S1. So, B and C should be loaded in S2 and S3 and the result will be stored in S1, that is A. So, B loaded in S2, C loaded in S3 and after it is added, the result is stored in temporarily in S1 and finally, it is saved in A, stored in A. Let us see some more. Similarly, this is a two set of instructions or two set of arithmetic operation that it is performing. In the first case, it is performing B plus C minus D, and in the next what they are doing, in the next they are adding F with the computed value of A. So, how we can do that? So, firstly add S1 S2, store it in T0, then sub T0 and S3. So, in S3 D should be loaded and finally, I add F with A. F is loaded in S5 and E is in S0. So, B is loaded in S1, C is loaded in S2, D is loaded in S3 and F is loaded in S5 and finally, once we compute, the result is stored in S4 and S4 should be stored to E. So, from S4 we have to move it to E and partially this result should be stored in A. So, we stored the result S0 in A. Let us see some example of load and store. So, this is an array A of 10. So, A is a location and is an array. So, in a consecutive memory address we have stored various data and in the 10th location what we are trying to load x minus A of 12. Let us see how we can convert this code. Firstly, this address 12th address, it is a 32-bit instruction. So, each instruction is 32-bit. So, each word is stored as a 32-bit. So, the 12th word will be 4 multiplied with 12. So, that is 48. So, we need to load the initial address of A in S0 and then we will be adding this initial address of A, that is in S3 plus 48 and that particular address, the word which will be having will be A12. So, that word will be loaded in T0, then x must be loaded in another register. Let us say it is loaded in S2 and we do S2 minus T0 and we store it in T0 and finally, this particular result is stored back in location A10. So, the address of A plus 4 into 10, that is 40. So, S3 contains the starting address of an array of this array A. So, this will be starting address plus 4 into 10 and this is starting address plus 4 into 12. So, S2 loaded with x and once we load this in T0, then this particular value, because in S3 we have loaded the address added with 48, which will be loaded in T0. And finally, we subtract it and store it in T0, and finally, this T0 is stored in this particular location. So, address of A10 will be S3 plus 40, 4 into 10, and then address of A12, as I said, will be S3 plus 48. That is what I have used it. So, to represent a C code, we have to use the following set of assembly language code. Let us see some examples of control constructs. So, in C, we often do this: if x equals to y, then do something, or x not equal to y, do something. So, let us see how we can convert this particular C code. So, if equal to, then we have to do this. If it is not equal, then you do something else. So, we take a branch instruction, which is branch if not equal. And what this instruction is doing? Branch if not equal, that means S0 is not equal to S1, then go to this level if it is not equal. If it is equal, then this condition will not be met. So, the next instruction will get executed. That is what we wanted. If x is equals to y, z will be equal to x minus y. So, branch if not equal. So, we are checking for not equal. If S0 and S1. So, in S0 and S1, x and y are loaded. If it is not equal, then go to this level, and if it is equal, then the next statement will execute. So, it is a sequential execution. So, if this statement, after this instruction will get executed. With this instruction, if this instruction, it is a branch instruction, and the condition here fails, the condition is not matching, S0 is not equal to S1. If that is so, then it will not go to this particular level, rather it will go to the next statement, that is sub S3 comma S $S0 S1. So, it will subtract S0 and S1. So, S0, as I said, will be loaded with x, and y will be loaded in S1, and z finally will be loaded with x minus y. So, that will be written in this label. Let us see some more C code. If x not equal to y, then z equals to x minus y, else z equals to x plus y. How this MIPS code can be written? Branch if equal. So, we are not checking for this, we are checking for equal. So, if it is not equal, then we have to execute this, and if it is equal, then this should be executed. So, I am first checking if it is equal. So, I am doing branch if equal. If S0 and S1, in a similar fashion, x will be loaded in S0 and y will be loaded in S1. So, I load x and y in S0 and S1, and I check whether it is equal or not. If these two are equal, then I go to label 1. That means, this else part now I am executing. If both these are equal, I am going to label 1 and I am adding x plus y, which is in S0 and S1, I am storing it in S3. And let us say if it is not equal. If it is not equal, then I have to execute x minus y. So, I am executing that. If it is equal, then I am going to label. If it is not equal, I will execute the next statement, and in the next statement I am doing sub, where I am subtracting S0 minus S1 and storing it in S3. And then I am directly going to jump to this label 2, LAB 2. That means, I will not execute this, rather I have to skip this, because this will be executed based on this level. So, after this condition is satisfied, that is x not equal to y, then I have executed this statement, and after this I will go to later part of the code and will not execute this. So, I am jumping it to level 2. MIPS support a limited set of conditional branch instructions, branch if equal, branch if not equal. So, these are also supported. Suppose we need to implement a conditional branch after comparing two registers for less than or greater than. Then what we will do? If let us say S1 less than S2, I will do this. If S1 greater than S2, I will do this. So, like this, if x is less than y, it should do this, else it should do other thing. So, there are some instruction set if less than. That means, we will set T0 to 1 if it is less than. That means, if S0 is less than S1, we will set T0 to 1, and then we will do branch if equal. If T0 now equal to 0, then you add, that is the else part we are going. If it is not equal to 0, that means x is less than y. So, we are doing sub, that is sub $S3, $S0, $S1. And similar way we have done in the previous thing, we are jumping to level 2 because we do not want to execute this particular statement. So, we can execute such kind of C code, such kind of high level language code into low level assembly language code using these following instructions in MIPS 32. So, MIPS 32 assembler supports several pseudo instructions. This I have already discussed previously, that are meant for user convenience, and but even if they are pseudo instruction, internally it has to be converted into some valid MIPS 32 instruction. So, some pseudo instruction we already have for branch less than. So, this instruction will get converted into set less than, set this $at if it is S1 is less than S2, and branch if not equal. So, this will be at, this will not be T0, this will be at branch if not equal $at 0. If it is not equal to 0, then go to level. So, the assembler requires an extra register to do this. This register is at, this register is at, and the register at is R1 is reserved for this particular purpose. Let us see working with immediate values in register. Small constants like in any programming language we need to add some constant value. So, those values are immediate values that we need to add. So, in such cases this can be specified in 16 bits, and it occurs most frequently, that is about 90% of the time you have to add some constant value. So, like a equals to a plus 16. So, how will you do it? Add immediate $S1 comma 16. Now, you want to subtract a value $S1 S2 1025. So, S2 in S2 you have to load y, and then finally, S1 should be stored in x. A equals to 100. So, in A you have to store this 100. So, S1 equals to 0, you add 0 with 100 and you store it in S1, and S1 A in S1 here. In case 2, we can see that how large constants that requires let us say 32 bit to represent. How will you do that? How to load such a large constant? So, it requires two instructions. One instruction is not sufficient to load it, and we require two instructions. The first one is load upper immediate. So, instruction that loads a 16-bit number into the upper half of the register, and then we OR immediate that instruction to insert the lower 16-bit. So, using these two instructions, we can load a 32-bit number into a register. So, a 32-bit number cannot be loaded with a single instruction, rather it requires two instructions to do this. So, load upper immediate. So, in the upper immediate, first we load this here and then OR with this 0x3333. So, we OR with this and finally, we get that entire thing. So, there are other MIPS pseudo instructions like branch if less than, branch if greater than, branch if less than equal, branch if greater than equal. So, while doing programming, you will see that you will be using many such pseudo instructions which is required for your programming. But all those pseudo instructions, when you run through any simulator, it will get converted into low level MIPS 32 instructions. These are some more pseudo instructions like move, load address, branch if less than equal, branch if greater than or equal, and load immediate. Let us see a simple function call. So, in a C function, when you write many functions, function is it is intended to do a particular function, like adding two numbers. We can simply add two numbers, or we can also write a function that will take the two numbers and it will add. It will take any two numbers and it will do the needful. Here in this case, it is a swap function. So, in temp, we are taking a temporary variable, integer type temporary variable, and then we are keeping a of k in that temp. Then a of k plus 1 is stored in a k, and in a of k plus 1, initially a k we have stored in temp and we are bringing it here. Let us see how this can be written using a MIPS 32 code. So, first we do mul immediate $T0, we add $S0, 4. So, S0 is loaded with index k, which index we want to swap, that index and the next one. S1 is the loaded with the base address of A, because this particular array we are taking. Then the address of A of k will be S1 plus 4 into that particular S0. What will be the index? In the same way we did it in the previous example. So, mul immediate will multiply S0 into 4 and it will be stored in T0. Then we are adding S1 and T0 and we are storing it in $T0. Then we load the two words. We load the two words and we store it in two registers, that is T1 and T2. So, 0 of T0, T0 is the base address where base address of A. So, and we have this added T0 with S1 where we have loaded the base address, and that is what is in T0. So, T0 of 0 means the first we will get this, whatever is the value of k, depending on that particular word will be loaded in T1 and the next word will be loaded in T2. Now, we simply have to store this particular word in this location and this particular word in the next location. So, this is what we have done. First, we are loading the word from 0 of $T0 into T1, loading the next word, that is $T0 plus 4 into T2. Now, T2 I have to store it in 0 of $T1, that is what I am doing, store word $T2 into 0 of $T1, and I have to store this T1 into 4 of $T0 and jump to return address $RA. So, we from the main program we came to a function, that is swap. We perform this operation and then we will go back to that function again. Let us see MIPS instruction encoding. All MIPS instruction can be classified into 3 groups in terms of instruction encoding. Based on instruction encoding, you can divide or classify it into 3 groups. So, the first one is R type, which is register type. It has got I type, that is immediate, and J type, which consists of jump. So, in an instruction encoding, the 32 bits of the instructions are divided into several fields of fixed width. We have already seen instruction encoding from a general perspective. In this case, we will be seeing instruction encoding for MIPS, and all instruction may not use all the fields, but those will be specified. Those are fixed fields. An instruction may use it, an instruction may not use it. Since the relative position of some of the fields are same across instruction decoding becomes very simple. So, as it is already known that this particular field from this particular position to this particular position will be this field, from this particular position to this particular position it will be the other field, and so on. So, the instruction decoding becomes very simpler. Let us first see R type instruction encoding. Here an instruction can use up to 3 register operands. So, there will be an opcode, there will be 2 source register RS and RT and 1 destination. As you know, there are 32 total registers. So, 5 bits will be specified for this. In addition to this opcode and registers, you will have a for shift instruction, the number of bits to shift can also be specified. So, this is this particular bit SHAMT. Let us say you want to shift a particular value right to these many position, that how much bit position can be specified in this instruction itself. And for that opcode, what is the function that is specified here. So, this is an R type instruction encoding. This is, as I said, 6-bit opcode, source register 1, this is source register 2, this is destination register, this is the shift amount, the amount of shifting you wanted to do, that can be specified here, and the opcode extension. So, if this opcode it say let us say 00000, then we will say that this is an ALU operation, and based on that then we will see which ALU operation it is, add or mul or div, sub, etc., etc. Let us see some example of R type instruction, add S1, S2, S3 like this. An example instruction encoding, let us say this S1, S2 and S1. So, these are source registers and this is the destination register. Recall T1 was R9, S1 is R17 and S2 is R18, and for add this opcode is 000 is for ALU and for add it is 100000. So, now if you see this encoding, so this here goes your opcode, that is 0000, and then the function goes here, that is 1000. First register is T1. What is the code for T1? It is R9, which is the destination register. So, 01001, this is R9. Similarly, S1 and S2 are the two source register. S1 is R17, this is 10001, and this is R18, which is 10010. Next, move on with the next type of instruction, which is I type instruction. It contains 16-bit immediate data value. Now, see, suppose and this total 16-bit is an immediate data, and you have a source register and you have a destination register. This is all you have, and you have a single opcode. So, for any immediate value, we do not require other fields, but see, these values are fixed. This is source, this is destination, this is opcode, but this 16-bit immediate value has changed for I type instruction. So, this is 6-bit opcode, source register, destination register, and this is 16-bit immediate data. Now, you see some of the I type instruction in MIPS 32. Load word. So, from this memory location 50 plus dollar is 5, it will load that particular word from this memory location into here. So, all these type of instructions are a I type instruction. So, let us see this example, load word $T1 $48 S1. What is T1? T1 is your destination register, and this one $S1 is your source. And what is 48? 48 is the immediate value, okay, and the opcode for LW is this 100010, and the function, this value will be this. So, let us see how this will be encoded. Now, this is the opcode that I have written here. T1 is R9. I have to load the word into this destination register, and S1 is the source register, which is R17. This is R17 10001, and this is my immediate value, that is 48 is loaded here. So, this is a kind of I type instruction. Let us go to J type instruction encoding. It contains a 26-bit jump address field, and this 26-bit jump address field is padded with 2 zeros, such that it can be extended to 28-bit, and an instruction like jump to label. So, when we give jump to label, so it goes to a 26-bit address. By adding 2 more bits, it becomes 28-bit, and we move there. So, this type of instruction is jump type instruction, 6-bit opcode and 26-bit jump address. So, now you see that there is a clear place. This is your source, this is your another source, this is your destination, and this can be a destination for some, and this is the immediate data, and this is the immediate data for the next one. But now, if you have to check the opcode field, you can check the opcode field for all from the first part, and of course, for some you have to check this. Some instruction require 2 register operand, like we said RS and RT as input, while some requires only RS. And get to know that only after instruction decoded. After the instruction get decoded, then only we will know that okay, it has got these many source register, these many destination register. And while decoding is going on, we can prefetch the register in parallel, may or may not be required later. So, what I am trying to say that we already know that this is a source, this is a source, this is a source. So, well in advance we can prefetch it, maybe we may not be requiring it, for a for this J type instruction, we will not be requiring this RS and RT, but in that time we can already prefetch it, because for this instruction and this instruction we might require it later. So, if we prefetch it, we may require it and we may save some time. So, similarly, this 16-bit address and this 26-bit address, immediate data, these are immediate data, some address, these immediate data are retrieved, and then we can do a sign extension to make it 32-bit. We already know what is sign extension. So, we can extend this to 32-bit, and if it is required later, it is fine. If it is not required later, it is okay, but we can do this. Now, what are the addressing modes in MIPS we have? We have register addressing, we have immediate addressing, we have base addressing, where the content of register is added to a base value to get the operand address. We have relative addressing here, and we have pseudo direct addressing. See, the 26-bit offset is shifted by left by 2 bits and then added to PC to get the target. Why 2 bit? Because 26-bit 2 more zeros we have to add, and then we add it to PC to get the target address. So, these are the various kind of, see, we have learned so many addressing modes, but MIPS uses only these. So, we came to the end of lecture 10, and next we will see some of the programming, some of the programs that we can do using MIPS.